All right. Today let's talk about doing a SPH based fluid structural interaction analysis. In this case, it's just a wave flowing against a post. I'm gonna do two different problems, but I'm just gonna demo one. One is with a thicker post, and one is going to be with a much thicker post, where the post itself will actually deform by quite a lot, and that's gonna look like something like this, where the wave is going to flow in and it's going to hit against something very soft, and that's going to generate a deformation. Load is going to be transferred to the structure, and it's going to deform the structure that way. So it's a sort of a Lagrangian method based fluid structure interaction analysis. Okay, and these are the quick results I'm going to show. We're going to do it as usual inside workbench LS-Dyna. I use workbench as usual for pre-processing. Together with all those prep posts, it gives me the option to basically generate an input file that is going to work well with sort of all kinds of problems, basically, right? Now, okay, so let's get started. So what we're gonna do here is that's just making sure everything's opened up, right? The first thing I'm gonna do is I'm gonna turn off this body interaction because this is gonna generate a single surface contact, which I don't really need in this case. And what we're gonna do next is let's go ahead and look at the components here. I'm gonna call this the outer outer housing. Sure. I'm gonna call this the post, and then I'm gonna call this piece the fluids or the water or whatever the situation may be. Okay. Now both of these bodies are inside this single component because I've essentially shared topology them together, so it's bonded on the bottom side, right? Now for the outside case, I'm going to assign a basically leave it as a steel material. For the post, I'm going to assign a plastic part to it. Hopefully I have it here. Yes, I do. It's a polycarbonate material, so it's much softer. Now for the fluid, the first thing we're gonna do is change the reference frame here from Lagrangian to a particle method. Now the particle method basically allows us to mesh the geometry as highlighted as a particle, essentially with SPH. Now, from within here, we want to define a few different things, right? So we want to define a man no, which is usually what's used to define a liquid material like water, right? In this case, you can see I basically have 1,000 row here that's sort of indicated. What we want to also generate is an equation of state, the EOS Guarnissen. The Guarnissen EOS basically help us sort of define the bulk behavior of the fluid. So together, these two things define the material for the water, and these are relatively published material. You can find out in different paper yourself. They usually stay pretty consistent in different paper that I've seen. These two the number are relatively consistent from there. Now, what we also want to do is to define a rigid wall that this thing is going to sit on. So what I like to do here is to define a coordinate system for the definition of the rigid wall, right? So what we want to do here is that we're going to define the coordinate system um, right at the bottom surface of this wall right here. And then what we want to do make sure is that the XY plane is parallel to the surface and the Z-axis is pointing upwards, right? So to do that, I'm going to adjust my principal axis until this is the case, um, like that. And then I'm going to flip Z so that Z-axis is pointing upwards, like that. Okay, and that's going to generate the coordinate system from which I'm going to define my rigid wall. In fact, we can go ahead and just do that part because I want this case to sit on top of a rigid wall, right? So what we can do now is go to ls pre and then attach a rigid wall. This rigid wall is going to call on the coordinate system which is generated, as you can see. Depending on which coordinate system I'm using, the rigid wall is always going to follow the XY plane, and then it's always going to be in contact with all body in the positive Z directions. And so this is what we're doing here. I basically use the bottom surface to create a rigid wall. All right. What we're gonna do next is let's go ahead and mesh the bodies, right? I think that's maybe a good time to start doing that. What we want to do here is let's go ahead and well, let's go ahead and just do these settings. I'm gonna set this to 100 millimeter. and I want to use a linear element. Oops, sorry. And then I think for the outer casing, what I want to do is to define a body sizing for this, and then make the size 50. And I want to make sure this thing is brick mesh, so I'm going to I'm going to generate a method and then attach this and then make this a multi-zone. Which is pretty much guarantee that this thing is brick mesh, and I can right click and generate mesh to test it out to make sure it's correctly meshed. And it's pretty pretty coarse, but it should be okay for the purpose of what we're doing. It's a pretty simple mesh for the most part. We're going to add a method for the fluid, and I'm going to define this as a particle-based method, so HPH, SPH. Right now, the SPH particle size matters a lot from the definition of analysis, right? So for this kind of problem, you really want the particle distance to be close together. From what I've been able to experiment and found out myself, right? Basically, I put a 7.5 in one problem. I'm gonna put a little bit closer in another problem. But what you can see is that once you do this, and if I generate a mesh on it, right, you can see this is a very dense particle. You can sort of see the particle distance are very, very small, right? I can make that distance bigger to really reduce the cost of the simulations. But what happens here is that it's actually going to be a lot less a lot less accurate, if we were to increase the particle distance. Essentially, when we do problem like this, what we really want to do is to get a mesh independent results, right? By gradually decreasing this number, and you can look at the results, and there's a few other parameter that within the control SPH and the section SPH card we'll want to be able to adjust to make sure we get a good result. But it is very sensitive to the particle diameter, right? So we want to pay attention to this. It's essentially based on the kernel function that we're going to talk about in a second. Okay, now with with this, right, I think it looks relatively good. We don't really need to set a lot of the sizing. It doesn't really do a lot. This diameter really is what's going to matter. Like for example, I can add a body sizing to this. If I add a body sizing to this, and then if I set this to something like 7.5 as well, it's not going to do much to the mesh. It basically doesn't really affect it, right? Uh, it's the particle dimension that's really going to matter the most. And lastly, what we want to do is to set a sizing for the post. The post is going to be the part that in an actual study I want to get a better sense of. So, but in this case, I can just make this thing cheap. I just want to make this 50 because I know this thing isn't going to deform a whole lot, right? This last one we'll just copy it by accident. I'll delete that, and I'll just mesh. Okay, this gives me the entire mesh structure that I'm gonna be working with. Okay, good. Now, what we want to do next is to create a name selection for this body right here. Body fluid. Now, the reason I'm doing that is because I'm going to define the contact between the fluid and the case and the fluid and the post, right? But as with any other SPH type of analysis, what we want to do is to create a nodal name selection from the body selection. And that's going to create this 200,000 nodes right here is going to be scoped to, you see all that nodes right there is going to be scoped, excuse me, it's going to be scoped to the, it's going to be the scope to the all the nodes on that body. And then I'm going to create a name selection ID, a body ID called 999. And this 999 is what I'm going to use to essentially define contact between these nodes and the two different bodies that we just talked about, right? Okay, so let's go ahead and do that. I've already written these cards, right? But what you want to do here is to generate a contact automatic nodes to surface cards, right? And what we wanted to do here is to make sure uh, that these two contact cards that I'm about to copy paste into my screen, right? You can see I have no set ID 999 against the body's 3, right? So in this case, my body should be 1, 2, and 3. So let me go ahead and turn off mesh. Right, body is number 1, number 2, and then the fluids should be number 3, right? So what we want to do here is to make sure our master ID set ID is going to be 1 and 2, right? And that corresponds to a master type of 3, which corresponds to the body to the part ID part type instead of a set, right? So 4 will be a set, 3 will be a body. Will be a part, sorry. So the part is going to refer to part number 1 and part number 2, and part number 1, number 2 is going to be the outer housing and the post, right? Which is what this automatic node surface content. Everything else in this card is relatively standard. You really don't you can model you can play around with the different value of these to see the behavior. Usually it's okay. You can maybe change this to soft 1 instead of soft 0, right? I'm sorry, so you can change to soft 2 instead of soft 1. But usually soft 1 is relatively recommended. It's a penalty base you can use for this kind of problems, right? What we're essentially doing here is that we're putting together all the nodes in the set 999, and we're gonna be put them in contact with the body number 1 and body number 2, right? Which are the outer face and the post itself, which is what our contact card is doing. Okay. All right. Once we have that, and the rest of the setup is relatively simple. What we want to do is to first define. Let's go ahead and define a couple other things. Let's do a control SPH start. So the control SPH. Well, let's do this first. Let's go ahead and generate the section first. The section is probably the easier thing to do. So I'm going to assign this thing to a section card here, and I'm going to call this SPH. And then I'm going to change the minimum and maximum length scale factor to 1. And that generate a constant smoothing factor, right? And the initial smoothing constant I'm going to set to 1.2. The 1.2 is the default recommended value. For SPH problems, right, the recommendation from literature is to set both minimum and maximum scale factor to 1. So you have a constantly smoothing scaling factor. So that doesn't change. And this gives you a really like a smooth response, as you can see in that video earlier, right? When the particle the diameter distance is small enough, it gives you a very smooth response in terms of how the fluid itself actually flows inside the model. Okay, now what we also want to do next is to generate a control SPH card. Now the control SPH card can be written inside this little window right here, right? But from my perspective, what I like to do is to actually write my own SPH card. As you can see, right? You see I have a bunch of these cards right here. One of my cards is called a control SPH. Is this number right here? Oh, I'm sorry, the section SPH. Control SPH is, oh, this is actually a mistake. I need to fix that. Oops. All right, okay, anyway, so the control SPH card, I'm going to use another one. So not from here. I'm going to grab another one. And then the control SPH, what we want to do here is to write this out, right? So the control SPH, as we will talk a little bit about, right? So the control SPH is basically a card that defines the various behavior of your SPH particles, right? So one of the key things to remember is that form 15 is used for fluids, right? It checks that the number of times the particle gets sorted. Usually that's a 1. A couple other important factor here is that what happens to the deactivated SPH particle, and SPH particle gets deactivated after the velocity exceeds say a certain value. In this case, it's like 20 meter per second, right? And there's a very important factor called artificial viscosity behavior, which are defined here. I just copy pasted from documentations. But basically, the artificial viscosity is a way to define viscosity for the fluid in a Lagrangian frame of reference. As opposed to defining viscosity, in a CFD software, this is basically how the program calculates the viscosity for the fluids. It's an artificial sort of type of way of doing this. And then you can sort of see the basic mathematics behind it. Now the Q1 and the Q2, it comes from this control viscosity card. Basically, your Q1 or Q2 value gets fed into the type of artificial viscosity method. You have two. One is the Monahan, one is the standard way. In this case, we're using the standard way for this kind of problem. Okay. Now with the control SPH here, right? What we obviously want to do is to generate a control bulk viscosity, right? The control bulk viscosity is the value that we're going to be using within the control SPH under the IVIS parameter, which is the standard of viscosity formulations, instead of using the Monahan one that's also available when IVIS is equal to 0. Okay, so both of these sort of defines the different behavior for the SPH particle as well as the artificial viscosity, which is critical to define for this kind of problems. All right. And for what we want to do next, right, is go ahead and generate a database card. The database card is going to be the one we use for basically extracting data. So this analysis is going to run for, say, 4 millisecond, right? It's going to run for 4 millisecond, and I'm going to change this to 0.01 milliseconds, so you get like 400 data points. It's give you a very smooth video in the end where you're capturing enough data from the model. Okay. Now with all of this, notice I'll control SPH here. I have a box ID 693, right? Now the box ID 693 needs to be a box that we want to define inside the model. So what this does is that it gives you a way to basically define an area upon which if a SPH particle goes beyond this area, it is automatically deactivated. Now in this case, I only did this because usually, just to show how it's done, right? What we can do here is set a coordinate system to global, right? Or I'm sorry, set a coordinate system to the local one, which is this one right here. And I'm just gonna type some value to some 350, 350. I don't know if you can see it. And then I'm gonna do negative 1,000, 1,000, and then I'm gonna do negative 100 and 2,000. As you can see now, this is the box. Now maybe this can be a little bit smaller, right? It doesn't have to be 2,000, maybe like 1,000. That's probably good enough. Now this box basically governs the SPH. Now if you might, so the 693 number, right? We're gonna have to check on this later. So let's take a look at it after we write out the input file. Okay, now with everything like this done, let's go ahead and just define a few other things to finish up the analysis. Now what I like to do is to generate an acceleration in the negative x direction, in the positive x directions. So what this would do is that you'll actually put the entire body. So the number should be it's this number right here. I'm gonna copy it. I'm gonna just copy paste it. Right here. Okay, you see, so the acceleration going upwards, which means there's a gravity force going downwards. And what I want to do with this is to generate a dynamic relaxation, right? And what that is going to do is that the dynamic relaxation is needed to preload the structure. So the analysis starts. Actually, you know what? Because I'm going to start this in transient, so I apologize. We don't need to do this. I forgot about that. Yeah, because we're going to start the gravity load at the beginning of the transient analysis. We don't actually have to preload it because what the gravity is going to do is going to cause the water to flow down, right, from this position, right. All the weight of the water is going to flow down and is going to flow into the post, and that's what the gravity load is for, essentially, right. And then because the rigid wall exists between the floor and the table, right, is going to sort of sit here. Now, if you want, you can actually fix on one. I can actually add a fixed support, say right here, if I really wanted to say I'm gonna fix the container so it doesn't move, right? All right, with this is pretty much everything we needed to do, right, for this analysis, to sort of set up this problem. Now let's go over real quick what we did, right? We set up the fluid material for the fluids. We set a reference to a particle that allows us to mesh this thing with a particle. We're going to convert the particle into a node selection set. That's going to be converted from a body name selection. This node is going to be defined with a 999 ID. The set ID is going to be converted into a contact automatic card that allows the set ID 999 to see the body 1 and body 2, which is the housing and the post respectively, right? And that generates the contact pair, and then we define the control SPH behavior we're going to use the control SPH to define the behavior of the SPH particle and its neighboring behavior and the kernel functions. And then we're going to use the control bulk viscosity to define the viscosity of the fluids, right? And then a couple of small things that we use a box here to define the limit of at what point does the particle automatically gets deactivated. In this case, this is mostly just for demonstration purposes. And then lastly, this analysis is going to run for 4 milliseconds and is going to transfer the units in terms of millimeter, millisecond, kilograms right here. That's it, right? And that unit system is going to be what we want to use to uh, uh, no, sorry, I think this, what was my units in this case? Hold on 1 second, let me double check. I think this unit system is MKS, I apologize. This unit system is MKS. Right. So we want to write out the input file in terms of MKS. Okay. Now, once I have everything set up, I have my content, I have my relationship between my SPH particle and my post. And then I also define the behavior of my SPH particle along with my section card for the SPH. To get the section card and the control card together really influences how the SPH particle behave under load, right? That is where the true quote unquote magic occurs within SPH, is that we want to correctly define both the section card and the control cards for SPH. Now, one more thing what we want to do here is that we actually might consider turn off the control cards. So let me show you what I mean. I'm going to go ahead and save this. And then I'm going to write out an input file, right? I'm going to call this input file, 1 second, let me find the right SPH. And then I'm going to call this demo DC SPH wave. Okay, now if we look at this problem with this card here, right? If we look at this card, I had to remind myself to change this. This got messed up. Now, if we look at this card right here, right? All right, 1 second, guys. I'm gonna go ahead and fix that since we're here. It does not hurt to go ahead and fix this because that's not supposed to be like this. There we go. All right, save it. I fixed that card. Now with the card we just generated, now because we're using the default control cards and default database cards, right? This actually creates a lot of different problems. So what I actually want to do is to change to deactivate all the control cards except for except for the control termination control time step. And what I actually want to do here is to change the TSS factor from 0.9 to 0.45, right? Because there's a big requirement for stability for this kind of analysis, right? So one good practice for this kind of problem is to change your TSS factor from the default 0.9 to something much lower, and it does require a little bit of experimentations, right? So you can see this is actually a number that I should have adjusted right here, which is called 0.45, right? If I change it to 0.45, it's actually going to make the model behave better, and it's actually make the model solve a lot longer, but it's going to actually help a lot in terms of stability for the model. And then one of the most important thing we want to deactivate along with all these contact cards is this contact hourglass, this control hourglass. This is really gonna mess up your analysis. Because hourglass control in this case really does not apply for SPH, so we want to turn that off. And if you need to apply hourglass control for the solid elements, you apply directly within the part, section, and material definitions, right? Not using a global control card. So remember to deactivate that, and once we deactivate that and we change the TSS factor to 0.45, this model is ready to go. And then we can just solve it, and what you can see, right, in the end is that you can sort of see a very smooth response, as you can sort of see from my previous video right here. If I can show it real quick, right? This sloshing post right here gave it a pretty smooth response because the particle is very, very dense, and the smoothing control is what worked pretty well for this kind of analysis. You get a pretty decent response, and we can actually probe for stresses on this post. This is a much better scene in a situation like this, right? If we look at something like this, you can see in this case, the particle size is actually a lot less dense. So you can already see there's some deactivated particle right there that shouldn't be like that. Okay, those are actually technically deactivated. because they're too far separated from the neighbors. So something like that we want to pay attention to in terms of the behavior of SPH when we are modeling with this kind of techniques. Okay, thank you very much. Hopefully this is helpful to you. A good thing to mention, right? I didn't go over this, right? The section SPH right here, the smoothing function that are used as part of the SPH method is something really worth looking into. But what I did here is basically a quick summary of the type of functionality within the section card. Over here, basically all we're doing is to define how the individual particle and their neighbor gets smoothed. The smoothing function that's defined within the kernel function is something we can define within a section card. And these are some common advice that I've researched and found that work pretty well. For solid mechanics problem, right, the min is usually 0.2 and H max is usually 2.0, which give you a way to adjust it during the solution. For this kind of fluid modeling, usually they recommend a constant smoothing scale factor which works pretty well as you can see in this model. Okay, thank you very much.